Welcome to the Sine Law, Lesson 3. In the previous lesson, we looked at examples 4 and 5 using the sine law. In the sine law, we can solve for angles or side lengths. So in one version, example 4, we solve for an angle. And in example 5 last time, we solved for a side length. And what we noticed is that if we're solving for side lengths, the unknown side length goes in the numerator of the first proportion, whereas if we're solving for an angle, the unknown angle goes in the numerator of the first proportion over its opposite side. So in the last problem, what we're going to look at is compass directions and how to solve word problems using compass directions. So to introduce compass directions is our first goal. So if we're using the compass direction, so example 6 says indicate each direction on the compasses below. We're looking at, first of all, at the direction of north 25 degrees west. Now, nautical degrees or directions are always used in relation to north and south first. So if we're looking at north 25 degrees west, what we would do is start at north, so north is right here, and then we'd move 25 degrees west from north. So if I go 25 degrees to the west, we're just approximating here, that would be roughly north 25 degrees west. South 70 degrees west, you'd start at south and move 70 degrees west from there. So 70 degrees west from the southern direction is roughly in that type of direction right there. And finally, south 15 degrees east, you'd start in the south direction, and then from there, move 15 degrees east. And 15 degrees east would be roughly that amount. So those are nautical directions as boats travel. All right, so let's read our last word problem here. Example number 7 says this: two lighthouses on shore are 12 kilometers apart. So generally what you want to do is just start somewhere and then refine it as you go. So if we look at this part, we've got two lighthouses. Don't mind this part at the moment. Two lighthouses, whatever they look like, they're 12 kilometers apart. So there you go. Okay. Next. From a boat's position in the water, it is 9 kilometers at a bearing of north 30 degrees west. Well, north 30 degrees west, here's north, and 30 degrees west would be roughly in that direction. And that's to lighthouse A. And a bearing of north 50 degrees east. Well, north 50 degrees east would be north and then 50 degrees east would look something like this to lighthouse B. So you'd want to ask yourself, where should I put that? Fortunately, I've done it somewhat accurately, but in some cases it may not be that the lighthouses were spaced evenly in your original proposal. But in this case, it kind of looks like that's kind of the direction that it's going to look like here. So it is north 30 degrees west to lighthouse A, and north 50 degrees west to lighthouse B. So that looks kind of like the problem that we have here. And it states next, what compass direction would the boat have to follow when leaving lighthouse B for lighthouse A? So let's put this a little bit more accurately onto this diagram here. So we've got a boat, we've got lighthouse A, and we've got lighthouse B. Okay, so as stated previously, to go from the boat to lighthouse A is roughly north 30 degrees west, and from the boat to lighthouse B is roughly north 50 degrees east, and we have a total of 12. And the more accurate that you attempt to draw these to scale, the better off you tend to be as far as understanding your answer. So 12 kilometers between the lighthouses, and the other direction that we have is that it is 9 kilometers from the boat to lighthouse A. So that kind of looks like all the distances and measurements that we have at this point in time. So what we're trying to do next says, what compass direction would the boat have to follow when leaving lighthouse B for lighthouse A? So really what we're doing here is we're recognizing that probably to go from lighthouse B to lighthouse A is going to start at north and go a certain amount of degrees west. So our final answer will probably be north and something degrees west. That's my prediction based on the proportion or my proportional drawing. So that's my guess. So we have some work to do. First of all, let's just start somewhere to see if we can understand what this question is asking for. We do know that this total angle here, because it's a composition of 30 and 50, is 80 degrees. So if we look at this triangle, It's always good to put compass directions on each vertex if you're solving these type of problems. So I put a north and south compass direction on each of these. We have a couple of opposites. 12 kilometers is opposite 80 degrees. And we also can notice, well, the angle that we can solve for in this particular case is the one that's opposite 9 kilometers, which would be this angle here. We can just call it angle B. So 9 kilometers is opposite angle B. So if I want to solve for angle B, which we might as well do, this would be sine of angle B, because the angle's in the numerator, over 9 is equivalent to sine of some other angle we know, which is sine 80 in the triangle, over its opposite side, 12. So in this particular case, we'd multiply both sides by 9, being careful on our calculator, and we'd have that sine B is equivalent to, again, making sure that you're in degree mode, sine B is equivalent to sine 80, hit equals, divided by 12, hit equals, that's your proportion, and now multiply by 9. So it's 0.738605. 0.738605, etc. So angle B is equivalent to the opposite of sine, which is sine inverse 0.738605, etc., etc. So angle B is equivalent to sine inverse of that proportion, 48 degrees. So this angle here is 48 degrees. Now, we have a little bit of work to do. One important thing to recognize in these compass direction problems is that sometimes you might be dealing with some parallel lines and some parallel line properties. So as was learned in a previous unit, we might want to notice, for example, that this angle here is also 50 degrees. Because, and here's the reason, we've got two parallel lines right here and here, and we've got the transversal. So those are called alternate interior. So those two 50-degree angles are equal to each other. We also might then, and this just takes some practice getting used to searching for these things and what may or may not be useful. You can also notice that this angle here has to be 40 because these add up to 90. So 40 and a 50-degree angle add up to 90. So if I was to zoom in on that area, it looks like this angle here is 40, but the entire angle inside the triangle is 48, which means that the remaining portion right here, which is itty bitty small, would be 48 minus 40, that's 8 degrees. So finally, what we can do is if that's 8 degrees, and maybe if I can try to represent this a little bit bigger, at this point we're kind of shaped like this, and we know that this is 8 degrees. Okay, then we know that this angle right here must be 82 because they have to add up to a 90-degree angle. Okay, so this angle right here, which is kind of the one we were looking for, is 82 degrees west. So in answer to the question, what direction would they have to leave from B to get to A? It would be the answer north 82 degrees west. So in summary, about the sine law, the sine law says that for any triangle, we have these proportions being equal. Sine A over side A is equivalent to sine B over sine B, etc. And here's the important thing. In order to use the sine law, you must know the measure of an angle and its opposite side. So here's an example. If I know that angle and its opposite side, the sine law may be useful for me. Key idea number 3, when using the sine law, always place the unknown side or angle in the numerator of the first proportion. So if we're solving for an angle, we'd use this version and we put the unknown right there. So use this when solving for an angle. If we're solving for a side length, we'd use this version and put the unknown right here. And key idea 4, boating or flying directions always start in the north or south direction, and then they travel east or west from there.